Hi, Chris Kuzmal here again. Today we're going to learn about the concepts of soundness and completeness. I often think of a cat on a table, and will the cat stay on the table? That means that the situation might be sound. But if the cat's going to stay on the table, it's probably not going to be exploring every square inch of the table. So it doesn't completely cover the entire table. That helps me visualize the two ideas of soundness and completeness. In order to understand it at a more precise level, I want to review, we've gone over these two slides before, but I want to go over notation and vocabulary again and just remind you that when we use lowercase Greek letters, then we're talking about logical sentences. When we use uppercase Greek letters, we're talking about sets of logical sentences. And at some level, that's a given set of logical sentences can be seen as a single logical sentence, which is where all the sentences are anded together. They're all one big giant conjunction, but that distinction is still, we usually still have the idea of a set of logical sentences. There's also a notion of a set of rules of inference, which really in this course we don't use too often, but it still comes up from time to time. We have a given set of rules of inference, and we refer to them using an uppercase Latin letter like A, B, C, or R. And then there's the symbol for entails, which is this little thing, the colon here. Don't be confused by the colon. This vertical bar followed by what looks like an equal sign. The double turnstile means that the truth columns match. The thing on the left has the truth column matched to the right. Although actually match isn't quite the right term because that would imply complete equivalence. And then provable means that the rules of inference allow us to derive from the left to the right of that symbol. So those symbols then help us say things like the set of sentences gamma prove via the set of rules R the sentence phi. And we've talked about this before. Now let's use those symbologies to define soundness and completeness formally. Soundness says that if delta allows us to prove phi, then delta entails phi. And completeness says that if delta entails phi, then we can prove phi from delta. So that's a little bit abstract. We try to move back and forth between this formal definition and an intuition. And so now let's go from this formal definition to sort of an intuitive comparison of what you can prove to what is entailed. So the left-hand box here has the concept of everything that is true is green there, everything that is entailed based on some set of premises. And I can prove, if I'm in one situation where my set of rules or my system of proving things is sound, then I may or may not be able to prove everything that is entailed, but everything that I prove is indeed entailed. So I'm sort of in the safe space. Things are sound, safe and sound. On the other hand, if I want to cover that complete table, if I'm that cat on that table, a cat that covers every square inch of the table, that cat's going to jump off the table, most likely. No proof, I can't prove that, but the intuition is that to be complete, it's kind of hard to stay on the table, to cover the entire table. And so here, if I can prove everything that is also entailed, then I can't see the table underneath the area that I've walked. And finally, it is possible, and the Fitch system does this, it is possible to be both sound and complete, but that just means that everything that you can prove is also entailed from a given set of assumptions. And that gives you both a formal and an informal definition of soundness and completeness for proof systems.